Hey everyone, welcome to this explainer where we are going to decode the deep science behind a sci-fi masterpiece that absolutely blew the minds of both Hollywood and the actual scientific community. We're talking about Interstellar, of course. Did you know that this film managed to accurately depict a massive scientific phenomenon on screen a full 5 years before it was actually discovered in the real world? So let's dive right in and explore exactly how fiction became reality. So, when the very first real-life photograph of a black hole was released to the world in 2019, the scientific community literally lost its mind. And why wouldn't they? The real thing looked almost exactly like the visual rendering we saw in the 2014 movie. It's kind of crazy to think about, right? It wasn't time travel, though. It was just the result of incredibly precise math. The mastermind behind this insane level of accuracy was Nobel Prize-winning physicist Kip Thorne. He literally fed Albert Einstein's equations into supercomputers just so the visual effects team could build an accurate image. The result was so groundbreaking that it actually led to the publication of 3 real, peer-reviewed scientific papers. Just think about that for a second. We got actual, real-world scientific breakthroughs from a cinema project. All right, moving on to Section 1, Deconstructing Gargantua. So why exactly does a black hole appear pitch black? Well, it all comes down to the event horizon. It's essentially this theoretical boundary around a black hole where gravity is just so insanely strong that not even light can escape its pull. And obviously, if no light can get out, that specific area is going to look completely dark to us. It is the ultimate point of no return. But then, how do you explain that brilliant, glowing golden ring swirling around it? We call that the accretion disk, and how it forms is super fascinating. First, the black hole's gravity yanks in surrounding gas and dust. Then, this matter starts swirling, kind of like water spiraling down a drain, but it's moving at 90% the speed of light. That extreme speed creates an unbelievable amount of friction, heating the matter up to millions of degrees and generating that iconic glowing heat. And this is where we run into a truly mind-bending concept: gravitational lensing. You might have noticed that the glowing disk doesn't just sit around the black hole's equator. It actually appears to wrap over the top and bottom too. That happens because the black hole's gravity is so intense, it actually bends the fabric of space-time itself, warping the light coming from behind it. Simulating this deeply complex mathematical calculation took months of dedicated supercomputer time. Let's shift gears now into Section 2, the warping of time. 1 hour equals 7 years. Now, that sounds like a total sci-fi exaggeration, but it's actually a direct application of Einstein's theory of relativity. Because Miller's planet was situated so incredibly close to the Gargantua black hole, it experienced gravity that was 130% higher than what we feel on Earth. And the rule of thumb here is simple. The stronger the gravity, the slower time moves. That's exactly why just 1 hour there equaled 7 long years back home. Now, you might be wondering, is this just a fun theoretical concept? Not at all. To put this into perspective, let's look at real-world GPS satellites. They orbit out in space, where they experience slightly less gravity than we do here on the surface. Because of that, their clocks run about 38 microseconds faster every single day. If engineers didn't constantly adjust for that time dilation, our GPS navigation systems would be off by 10 kilometers every day. Imagine trying to drive with that. When you compare the time flow on Earth against Miller's planet and our own GPS satellites, the takeaway is absolutely crystal clear. Fluctuating levels of gravity directly manipulate the flow of time. High gravity, time slows down. Low gravity, time speeds up. It's a proven mathematical reality. That extreme gravity had another terrifying side effect, too. Gargantua's massive gravitational pull created immense tidal forces on Miller's planet, ripping up waves that were 1.2 kilometers high. Because the planet was tidally locked to the black hole, those towering waves, which looked literally like moving mountains, crashed down relentlessly every 1.7 hours. Now let's explore Section 3, Engineering Deep Space Travel. We all know space travel is tough, but it's not just about rocket fuel and physics. Prolonged exposure to zero gravity is absolutely devastating to the human body. We're talking severe bone density loss, rapid muscle atrophy, and dangerous cardiovascular deterioration. Our bodies simply weren't designed to survive in a weightless vacuum for years on end. So how do you solve the zero gravity problem on a decades-long mission? Centrifugal force. The Endurance spacecraft was brilliantly designed like a giant spinning wheel. As it rotates around its central axis, it generates an outward force, effectively simulating artificial gravity along the outer rim. And the coolest part? This isn't a new Hollywood idea. It was first proposed by Russian scientist Konstantin Tsiolkovsky way back in 1903. Okay, let's talk about that wormhole near Saturn. It's basically a theoretical shortcut through space-time. The easiest way to visualize this is to imagine the universe as a flat piece of paper. If you have 2 points that are incredibly far apart, you just fold the paper in half and punch a hole straight through. Boom, you've instantly bridged a massive cosmic distance. There is a major catch, though. While Einstein's math absolutely permits wormholes to exist, natural ones would collapse instantly the moment they form. To keep a wormhole stabilized and open, you would need hypothetical exotic matter that literally has negative mass. Sounds impossible, right? Well, theoretically, quantum physics allows for negative energy density through something called the Casimir effect, so it's not entirely out of the realm of possibility. That brings us to our final frontier, Section 4, Humanity's Interstellar Future. A huge question people always ask is, could you actually survive falling into a black hole? Well, if you fall into a normal-sized black hole, the gravity pulling on your feet would be so much stronger than the pull on your head that you'd be lethally stretched into a noodle. Astrophysicists literally call this spaghettification. However, a supermassive black hole, like Gargantua, is so incredibly enormous that the tidal forces at its event horizon are actually much weaker, meaning you could theoretically cross the boundary alive. But what happens once you're inside? The movie gave us the Tesseract. Since absolutely no data can escape a black hole to tell us what's in there, the creators leaned into string theory, which suggests our universe might actually have 10 or 11 dimensions. The Tesseract was a brilliant creative visualization of these higher dimensions, portraying a space where time isn't just something that passes, but a physical dimension you can actually navigate backward and forward. All of this high-level science ultimately points to a very urgent reality. The late great Stephen Hawking famously warned that humanity must become a multi-planetary species within the next 100 years. Between climate change, rapid resource depletion, and exploding population growth, we are eventually going to have to leave Earth to ensure our survival. So, what are our realistic stepping stones to the stars? It starts close to home with the NASA Artemis moon base and SpaceX's push for Mars colonization. But reaching distant star systems like Proxima Centauri, that's going to take thousands of years. For that, we're going to need to build massive, self-sustaining habitats known as generation ships, or O'Neill cylinders, where entire generations of humans will be born, live, and die in transit. Through all this incredible science, though, there is a profound thematic takeaway. The ultimate variable in all of this is love. Now, science obviously can't quantify or measure it, but love is the fundamental emotional connection that truly transcends time and space. It's the core evolutionary motivation that drives us to push boundaries, explore the unknown, and fight to survive against impossible odds. We've unpacked how gravity, time, and the complex laws of physics shape our universe, and how fiction can beautifully mirror cutting-edge science. But as we wrap up this explainer, I want to leave you with one final thought. Knowing all the dangers and the immense scale of the cosmos, if you had the chance right now, would you board a generation ship to the stars? Think about it. Keep that adventurous spirit alive, stay curious, and I'll catch you next time.